In this segment, we're going to talk about transformers. Now that we've introduced the attention mechanism, we can see how attention is actually a very powerful tool that does more than just let us look back at the input in seek-to-seek models. It can actually be the foundation of a whole new way of thinking about encoding sentences that's really actually going to be the basis for the way that NLP is done these days. So if we think about what we were building up when we talked about LSTMs, we had this idea of LSTMs as transducers. And one way we could use LSTMs, particularly bidirectional LSTMs, was a way to convert sort of word embeddings out of context into context-aware representations that have now looked at the words on either side. And we haven't talked about them much in this class, but convolutional neural networks can do something similar with convolutional filters. These filters look at things around kind of whatever position you're at in your sentence, and by having filters of different widths and many different filters, you can learn features that look at kind of the input locally, but more than just a single word. All right, and so what a transformer is going to be is a third architecture that allows us to do this using attention. And the key idea is going to be something called self-attention. And let me just motivate here what we want to be able to achieve with this self-attention mechanism. So if we have the sentence, the ballerina is very excited that she will dance in the show, we could think about how exactly we want to contextualize this sentence and what kinds of interactions we might need to capture. So for example, pronouns like she typically need to be informed about whatever their so-called antecedent is, the thing they refer to. And so in this case, it would be really useful for a neural model to somehow be able to associate she and ballerina so that we understand that she has the property of being a ballerina, right? And both she and show here probably should know about the verb dance. This is like a kind of event that these are arguments of. And so, the kind of word sense of show depends a lot on dance. And if she is dancing, that tells us, again, something about the properties of her, right? So generally, when we have ambiguous words or words that could mean different things, these should look at the context as well. Now, the kind of final effect is that we want words to look at this context syntactically. We don't just want to look at local kind of what are the words on either side like CNNs do, but we want these words to be kind of aware of syntactic dependencies. And these often go kind of farther in a sentence than we might easily be able to capture with something like LSTMs or CNNs. And so the problem is that this is our kind of view of how this contextualization operation should work from a linguistic perspective, but LSTMs and CNNs don't do this. So this is what we want, and this is what these models give us to a kind of first approximation here. So the kind of operation that we're missing here is the ability to get some amount of information over long distances. And obviously just kind of looking at a whole big chunk of text and saying, all right, all this stuff should be useful for contextualizing she, that's maybe a little too ambitious, or it's a little bit hard for a model to sort through. So the idea here is going to be that she is only going to depend in some sparse way on the whole context that it occurs in, right? It might have to look very far away to figure out basically there might be words that are far away that impact its semantics or what representation we should have for it, but it's not going to be every word, it's just going to be some words. So this is the idea behind self-attention. What we're going to think of is each word in a sentence as a quote-unquote query vector, like what we had in the decoder for sequence-to-sequence models. And then each word in the sentence is also going to be a key, or we're going to think about it as one of the vectors from the encoder. And so each word is going to be able to attend to every other word. And so what that looks like here is great. We're going to extract this vector and call it x4. And then x4 is going to look at every other word here and produce a new representation of itself, x4 prime, based on an attention computation over all these words. So what does that look like? So in this case, we're using the dot product as the attention scoring function, let's say. And so we compute alpha ij, the attention weight for like basically word I attending to word j, as the softmax over scores xi transpose xj. And then we can form a new representation xi prime by just summing over the values of j and treating these alphas as weights. And so now we're summing over all the xj weighted by alpha ij in order to produce a new representation for x prime I. So basically, each word now produces a distribution over all the other words in the context and then sums those up, weighted according to that distribution, and produces a kind of new version of itself. And so just one copy of this might not necessarily allow us to achieve what we want. Because we want to be able to look at several different words of context, and it's often pretty hard to get an attention distribution to like really nicely place, 40% mass here and 30% here and 20% here. That's a little bit hard to set up. So instead what we do is we have multiple copies of this process ongoing, which you can think of like different convolutional filters in a convolutional neural net, just kind of more oomph to the model that lets it kind of capture more effects. So what we do is we're going to swap out this attention computation we had above with this bilinear form where we have a WK weight matrix, where K is an index now over the so-called attention heads. So these are really just different independent copies of this calculation. And then we also introduce a VK to transform each xj when we're taking this final weighted sum. So again, on the bottom right over here, we're summing over the kind of other word indices, j. We're taking xj, we're multiplying it by just a matrix associated with this head, and then we're weighting that by the weight for this particular kth attention head, between I and j. All right, and so this kind of gives us a big stack of vectors associated with this particular position, and one from each attention head. And so now we can think about how this relates to the earlier example, and imagine that one head was able to achieve something like this. So what basically we're kind of looking at here are weights associated with she here. And these two heads, the first one lets it kind of look back at ballerina. The second one lets it look forward at dance here. And if we combine these, we see that it's able to both kind of attend to nearby stuff. It's able to attend to semantically related things, or like I said, the antecedent of this pronoun. And by having these multiple heads, again, we get a lot more power out of this model to capture complex interactions between this word and its context. So this self-attention idea is the foundation of the transformer architecture. So this diagram looks a little bit complicated, but really all that's going on here inside the gray box is that we have a so-called multi-head attention layer, which is what we just looked at. And we have a residual connection kind of across that layer, so meaning we just take the input vectors and also add them into the output of this module, and then we just have another feed-forward layer on top of that. So transformers are kind of alternating multi-head self-attention and feed-forward blocks with some kind of layer normalization and other tricks going on there to make them train well. So the one other piece here is this thing on the bottom, the positional embeddings. And the reason you need these is because, as we've described it, this self-attention mechanism doesn't actually know anything about what words are close to each other. For example, it had no way of knowing that she and dance or she and ballerina were not right next to each other or were not even farther away. We need to introduce some notion of position into the model. So basically what happens there is that the position is somehow encoded into a vector that is then itself used by the model. So position kind of isn't directly like built into the architecture, but it's instead stapled into the embeddings. And so there's a couple ways to do this. In their original work on transformers, Vaswani et al. Looked at having sines and cosines of like different frequencies as sort of basis functions, basically for this kind of positional encoding. It turns out you can also do pretty well by just like associating each integer index with a particular embedding. That does mean that it's hard to generalize to new indices. You can't train a model on sentences up to length 50 and then have it work for length 51, because you'll have to embed, index 51, and you have no idea how to do that. But both of these techniques kind of work. And so this is the overview of transformers and self-attention, and we see how this idea that we've built up here can let us build this new kind of flexible layer. And so we're going to talk about what transformers can do more later in the course, but this is one of the more important developments in terms of enabling both very successful sequence-to-sequence systems as well as large pre-trained models like BERT and GPT. That's the end of this segment.